Welcome back. As we discussed in the earlier sections, one of the nice features of a quadratic function is that it will either have an absolute maximum value if its graph has the shape of a parabola opening downward, or it will have an absolute minimum if its graph has the shape of a parabola opening upward. In this section, we're going to be looking at some models where the equation turns out to be a quadratic equation, and so we'll be able to maximize or minimize these functions. We're going to start off with some examples involving profit, revenue, and cost. These are kind of typical sorts of examples that you'll see when you get into a calculus class as a sort of a function that you might want to maximize or minimize. A couple of things just to begin with here. We are going to first talk about our revenue function. The revenue function, which I'm calling capital R of X, that's the amount of money that I make from selling X items. So here, X is the number of items that I'm going to sell, and R, that will be the amount of money I make from selling all of those items. Now, of course, these items have a price, and the price is P dollars. So for our revenue, it should just be the price that we're charging times the number of objects that we're selling. Our revenue should be just P times X. Now, of course, we're going to make sure that whenever we write our revenue function, that it's a revenue function just of a single variable. So what we'll need in addition to this formula for creating a revenue function, we're going to need what's called a demand equation. And if you take an intro economics course, you will hear all about demand equations. Those would be an equation that makes a relationship between the number of items that we sell and the price that we're selling them at. That's what a demand equation is. It gives the relationship between price and how many items that you'll sell at that price. Now, of course, our revenue equation doesn't take into account any of the costs that we've incurred making these items. So you might have another function, a cost function, C of X, and that would be the cost for you to make those X items. And so if you're interested in profit, how much money did you actually earn from this? That would be how much money you took in minus how much money you had to spend making those items. So our profit equation will just be our revenue equation minus our cost equation. Okay, so in this example, we have some object, and when we sell that object for P dollars, we will sell X objects, and the relationship, our demand equation, is given by this. That X, the number of objects that we'll sell, will be 40 minus 1/5 times P, times the price that we're selling those objects at. This, of course, you can also rewrite this equation if you wanted to rewrite it in terms of P. You could multiply everybody by 5, and then bring the P over to the left side and the 200 over, the 5X to the other side. So these are both equivalent ways of me expressing the relationship between number of items sold and the price that we're selling them at. Okay, so the first thing that we want is our revenue equation, R of X, and our revenue equation is just the price that we're selling things at multiplied by the number of things that we're selling. And this is where we need to remind ourselves, of course, that if we want it to be R of X, revenue as a function of X, then we want only one variable. And here I have two. I have P, the price, and X, the number of objects. So that's where I'll use my demand equation. I know that P is the same thing as 200 minus 5X. So I'll be able to replace P with 200 minus 5X. And that gives me my revenue equation of 200x minus 5x squared. Or if I write it as negative 5x squared plus 200x, there we go. And one thing that we can see right away, and this is the answer to part B, that this is an equation of a parabola that opens downward. And the reason we know it's a parabola opening downward is because the coefficient for the x squared is negative. Remember that whatever the coefficient is for x squared, that will tell us whether the parabola opens up or opens down. And so it's opening down because the coefficient of x squared is negative. And so you know that when a parabola opens downward, that wherever the vertex is, that would be the maximum value, the absolute maximum. So here we know for this equation, this revenue function, that it is its graph would be of a parabola opening downward. So that means that we'll have a maximum revenue and not a minimum revenue. And that also means that we'll have our maximum revenue wherever the vertex is. So the follow-up question, of course, would be, if we wanted to maximize our revenue, how many objects should we sell, and what's the price, and how much is our revenue from selling those objects? So all of these questions that we have here in part C really boil down to us finding our vertex for this parabola. Once we know where the vertex is, we will know the value for x and for revenue, where we have our maximum revenue. And then once we know that, we can figure out what the price would have to be for these objects as well. Now, when you're thinking about finding your vertex, you have to think strategically here. And so you know you have a bunch of options. One of the options, of course, is completing the square, which you could do. Another option would be finding x-intercepts and using that to help you find the vertex. And that's what I'm going to do here, because you'll notice that we already had r of x in factored form at that second line. And that means that we could easily find the x-intercepts for r of x. So for here, I'm going to start off by finding my x-intercepts. And I'm going to do that by letting r of x be equal to 0. And because we had r of x already written in factored form, then it's easy enough for us to find out where those x-intercepts are. So either 200 minus 5x is equal to 0, which gives us x is equal to 40, or x is equal to 0, which gives you x being 0. So your two x-intercepts, you have one of them at the origin, 0, 0, and the other one is at the point 40, 0. Now, the thing that we know, of course, is if we have two x-intercepts, that the x-coordinate for the vertex should be right in the middle. And so if our x-intercepts were at 0 and at 40, then the vertex should be right in the middle, where x is 20. And once we know where the x-coordinate is for the vertex, we can find the y-coordinate for the vertex by putting the x value into our function. Because, of course, the y value is exactly what the revenue function gives you. So if you wanted to know the y value for your vertex when x is 20, that's your revenue function when x is 20. And if we go back and put 20 into our revenue function, either the factored version or the unfactored version, it really doesn't matter, we'll find that our revenue is $2,000. So a couple of things that we found out. Number one, we know how many objects we should sell. That's what x represents. We also know what our revenue is. That's r of x. The other thing that we need to know is what is the price, and that is P. And so if we wanted to know what P is, well, we can go back and use the demand equation that we had. Remember that we have that demand equation that makes the relationship between P and X. We know that the relationship is P is equal to 200 minus 5X. So now that we know what X is, we can say that P, our price, should be 200 minus 5 times X, which is 100. So I sell 20 items for $100 each to get my maximum revenue of $2,000. So this isn't too terribly tricky. We just, of course, have to be clear on what all of our variables represent. X being number of items, P being price, R being my revenue. So when I find that X is 20, that's how many items I'm selling. When I find that P is 100, that's the price for each item. And when I find that revenue is 2,000, that's my total revenue for selling those 20 items. And that should be what I do to maximize my revenue. Now, we've got a follow-up question here where we now have a cost equation given to us. And this is one that we probably could have created the equation ourselves if we had just had the little sentence above. Fixed costs of $640. That means that we will always have a cost of $640 no matter how many things we produce. That's why in our cost function, 640 is the constant term. And every item costs $20 to produce, so we'll spend $20 times the number of items that we produce, or $20 times X. That's where our cost equation is coming from. Now, what we want to do is use that to come up with our profit equation. And we already know what our profit equation is. It should be just our revenue function minus our cost function. And we had those. We had that our revenue function, that was negative 5x squared plus 200x. Our cost function, that's 640 plus 20x. And then when I simplify that, I have negative 5x squared plus 180x minus 640. And again, the same follow-up question as before, how do we know that we'll have a maximum profit and not a minimum profit? Well, that's because P of X, the graph of that is, again, it's a parabola opening downward. And the reason that we know that is because the coefficient of x squared is negative. And of course, if the coefficient of x squared is negative, you're a parabola opening downward. And if you're a parabola opening downward, then you'll have a maximum value at that vertex. And it will be an absolute maximum, the largest y value possible. All right, so no surprises here as to what we'll be doing next. Now that we have our profit function and we know that it has a maximum somewhere, we will want to find what the maximum profit is, how many items we sell it for, and what the price is. And so what I'll do here is, again, thinking about our profit equation that we had P of X being negative 5x squared plus 180x minus 640. You could try, if you wanted to factor this and try to find X-intercepts. I suppose that would be an okay idea. I don't really know if that's where I want to go with this. I think instead I'll probably complete the square because that's probably going to be faster for me than solving for X in this case. So there we go. So out of the first two terms, I've factored out the negative 5. And as far as the amount that gets added, half of negative 36 is negative 18. And negative 18, when you square that, that's 324. So 324 is the amount being added and then subtracted. And of course, I need to remember that when the 324 leaves the bracket, it'll need to be multiplied by that negative 5 that's in front. And when I do that, negative 5 times negative 324 is 1,620. And then just finishing things off here with my completing the square. So that bracket x squared minus 36x plus 324, that is the perfect square of x minus 18 all squared. And then positive 1620 minus 640 gives me positive 980. So that means we know where our vertex is. So our vertex is at the point 18, 980. And of course, remember that the x coordinate here, x, that represents the number of items we sell. And the y coordinate, that is our profit. This is our profit from selling those 18 items. So I know that to maximize profit, I'm going to sell 18 items. And I also know that the maximum profit is $980. And of course, the other part that we wanted to know here, in addition to how many objects should we sell and what is our profit, we also wanted to know what was the price for selling these items. And again, just as we had before, the relationship between X and price is given by that same demand equation that we saw at the very beginning. So again, we have that relationship between P, our price, and X, the number of objects that we sell. And we can use that to find that the price per object is 200 minus 5 times the number of objects sold, which turns out to be 110. So $110. So there we go. As it turns out, if we wanted to maximize our profit, we'll need to raise our price a little bit. If we just were interested in revenue, it was $100 each. Now we'll charge $110 each. But because of our costs, we're making a little bit less. We wind up with a profit of $980. And now just a little geometry problem. These sorts of farmer's field problems, you'll see them again and again in calculus, in large part because they're nice enough equations that are easy enough to work with. So here we've got ourselves a restriction of 3,000 meters of fencing material to work with, and our goal is to make 3 enclosures that are all the same area. So that means that we want them to all have the same individual dimensions. So I'm going to just start labeling my diagram here. I have x's that I'm using for the one side length and y for the shared side lengths. And our 3 enclosures, they are sharing some sides. So I'll first start off by defining my variable x and y. So I'm going to let x and y be the length and width of each enclosure, with y being the shared side. And we should also indicate our units here. Our side lengths are being measured in meters, so there we go. So x and y, that's the length and width of each enclosure, with y being the length of the shared side. And so what we're interested here is maximizing the area of each of our 3 enclosures. And for each enclosure, it's a rectangle, and area of a rectangle is length times width, x times y. Now, of course, this is not something where we can maximize right away, because this is not a function of one variable. It's got 2 variables in it, x and y. Now, conveniently enough, though, we do have that restriction that we haven't done anything with yet, which is that we have 3,000 meters of fencing material in total, so that all of those side lengths, those 6 x's and those 4 y's together, need to add up to 3,000. And I can do sort of a similar thing that I did with the demand equation before, where I was able to use it to write my revenue function in terms of one variable, and I'm going to do the same sort of a thing here. I'm going to take that equation that we have relating x and y, and I'm going to solve for y, so that now I can say, well, that area equation that I have is now a function of x. Instead of x times y, it's x times 750 minus 3/2 x. And one thing that we can see here is that this would give you a parabola that's opening downward. I'm not going to be working with the expanded version of this function. I'm going to be using the factored version on the next slide. But if you were to expand it out, you'd see that the coefficient for x squared is a negative, which means that a of x, the graph, would be a parabola opening downward, which means that it should have a maximum value rather than a minimum value. So we do know here that there is a maximum area, and it should happen at wherever the vertex is. Now, as I said, I'm not going to use the expanded version of a of x, because I notice here that I have the factored version, and if you already have a of x factored, then you can find the x-intercepts, and if you can find the x-intercepts, then you can easily and quickly find the vertex. So if I were to start out with finding the x-intercepts, or in other words, letting a of x be equal to 0, that happens when we have x times 750 minus 3/2 x equal to 0. And that gives us two solutions, one of them being that x is 0, and the other being from 750 minus 3/2 x equal to 0. And when we solve that, we get x being 500. So for this parabola that we're talking about, it has two x-intercepts, one of them at the origin, and the other at 500, 0. So that means that the vertex is at that midpoint between 0 and 500, which is when x is 250. And now, two things that we can find out. Now that we know the value for x for our vertex, we can go back to our area equation, and now that we know what x is for the vertex, we can use that to find out our maximum area. And so that's what I'll do next. I'll use my area equation to say my maximum area. And that would be my area function when x is 250. And if you were to go back and put 250 into your area function, either the expanded version or the factored version, it won't make a difference as far as the calculations go. It would still give you the same value when you evaluate that function. And when I did that, I found 93,750. So each enclosure has a maximum area of 93,750 square meters. Now, we're not finished yet, of course, because remember that when we're answering a word problem, we need to go back and make sure that we've answered all of the questions. So here we've given what the maximum area is for our enclosures. Each enclosure, 93,750 meters squared. But we also need to go back and remind ourselves that we were asking for two things in this question. Number one, what was the maximum area? And number two, what are the dimensions? So now we'll answer the second part of the question, the what are the dimensions problem. And we already know the x-coordinate for the dimensions. And so to use the relationship that we had between x and y, we can use that to find the y-coordinate for the dimensions of our enclosures. So now we'll do that. We know that y is equal to 750 minus 3/2 x, and x is supposed to be 250, And so you can find that y is 375. So that means each enclosure measures 250 meters by 375 meters, where 375 meters is the length of the shared side. And there we go. Those would be the dimensions that we would need to maximize our area. So if we were to go back and let each of these x values be 250 and each of these y's be 375, that would use up all 3,000 meters of our fencing material, and our 3 enclosures would be as large as possible. They would all have that same maximum area of 93,750 square meters.